Bienvenidos. Welcome back. In this video, we are going to give a general overview, high-level overview of what a mixed integer programming problem is, and we are going to introduce some of the ideas of the methods that we are going to describe in the following videos. But essentially, in this video is just to give you a clean and a very precise idea about mixed integer programming models. And it's going to be a little bit abstract, but the core idea is that you get the core concepts here. So in general, a mixed integer programming problem can be defined in the following way. In general, a mixed integer programming problem will have two types of variables. One type of variable that we are going to call x these variables are going to be non-negative and integer. And another type of variables that we will call y, that these variables we only require to be non-negative, meaning that they can be fractional, they can take fractional values. And the reason why we call these problems mixed integer programming problems is because we have two types of variables, integer variables like x and continuous variables like y. And then in the objective function and in the constraints, we will identify what terms in the objective function are related to the integer variables and which terms are related to the continuous variables. So Cx is related to the coefficients and variables that are integer, and xy are the coefficients are the terms in the objective function value that have the continuous variables. Similarly, for the constraints, the constraints, we will have a matrix related to the integer variables and a matrix related to the continuous variables. And the right-hand side is going to be any parameter that we can have, and you can always formulate the problem as a less and equal constraints. So this is, in general, a mixed integer programming model. And from this general definition of mixed integer programming models, we can define special classes. For example, if the set of integer variables are empty, meaning we don't have integer variables, so we will only have continuous variables. So in this particular case, where we will maximize hy, and the constraints are going to be defined by this matrix gy less than equal to b and y greater than equal to 0, that's a linear programming problem. So when we don't have integer variables, and we just have continuous variables, that's a linear programming problem. And in the other extreme, it is possible that we don't have continuous variables, and we just have integer variables. So in this particular case, our objective will be to maximize Cx, and the constraints are going to be defined by the ax less or equal to b, and x being non-negative and integer. So that's a pure integer programming problem. And the general case is when you have both integer variables and continuous variables. So let's just to fix ideas about what is happening when you have MIP problems where you have integer variables. Let's consider this graphical representation of a problem that has two variables. The x variable is defined by this axis and requires to have integer variables, and the y variable is continuous and requires and is defined by this axis here. And let's assume that these blue lines define the constraints of your problem. And the direction of feasibility of these constraints are defined by these dark arrows. So if we take the LP relaxation of this problem defined by these constraints that we have here, any solution that we have here in this polyhedron will be a feasible solution for the LP relaxation. And the LP relaxation means that we are relaxing the constraint that requires that the x variable be integer. So now we are assuming that x can be continuous. We also have that y can be continuous, and these define this region here that we call the LP relaxation of this MIP problem. But when we impose that x is integer, so for x equal to 1, what are the possible values of the y? The possible values of the y variable given these constraints is this red line here. When x is equal to 2, the possible values of the y variable given these constraints is this red line, and so on and so forth. So these red lines are the possible solutions of this MIP formulation where x is required to be integer and y is required to be continuous and non-negative. So in the case when we require both variables to be integer, we have a similar situation, but in this case y is integer and x is integer. So again, these blue lines represent the constraints of the model, and the black arrows represent the feasibility direction. So the LP relaxation is all these polyhedron here inside, where we assume that both variables are continuous. If we impose the integrality constraint, then y and x needs to be integer. So in this particular case here, these dots means that x is equal to 2 and y can be equal to 1, 2, 3, and 4. And when x is equal to 3, then these are the possible values of the y variable. So the integer solutions for this problem are all these red dots that we have defined here. So this is just to give you a picture that when we are talking about MIP problems that they have both integer variables and continuous solutions, you will get a problem in a higher dimension that some of the variables will be integer and you will get hyperplanes of solutions of the continuous variables. And when we have a pure integer problem, we only have the integer values of the variables. So in mathematical programming or mixed integer programming, which is the main topic of these videos, the idea of solving MIP problems is to use the LP relaxation. So even that sometimes linear programming cannot solve the integer solution, we are going to use this, what we call the LP relaxation to solve the MIP problems. So as you saw in the past, when we formulate the assignment problem as a linear programming problem, this assignment problem has a special structure, and that's why we call the assignment problem with a perfect formulation, because by using linear programming we were able to solve the integer solutions. But that's not always the case. There are some problems, as when we add the budget constraint to the resource assignment problem, that we break that particular structure that allows to have integer solution, and now we need special methods to solve the MIP model. And in this particular video series, we are going to talk about two methods. One is branch and bound, and the other one is called cutting planes. And again, I need to emphasize that we are going to discuss this method just to give you a general overview about what is happening when the Gurobi Optimizer is solving a MIP problem. But you don't need to worry about the implementation of this method, because this is already coded by world experts on mathematical optimization and MIP. They have implemented the versions of these approaches to solve the problem. The only thing that you need to do is to have an accurate representation of your problem as a mixed integer programming problem formulation. So in the next video, we are going to discuss the branch and bound method. So thank you very much for your attention, and see you at the next video.